All right, so you might remember free body diagrams are simply a diagram that shows what?
Magnitude and direction of all forces acting on an object in a given situation.
You took the words right off the screen, Joey. What does that mean? Relative magnitude, what does that mean? It means the bigger forces have bigger arrows, and the directions match the directions they're supposed to, right? Bigger forces, bigger arrows. It removes all of the sort of the distractions in the problem. And it should allow you to sort of figure out the overall net force, which we'll talk about very soon. I'm going to skip through this stuff here. You've seen it in grade 11, and we've just kind of talked about it. So let's just jump right to things. The book is at rest on a tabletop. Diagram the forces acting on the book. So you should have just weight force, or force of gravity, and you should have normal force. And those arrows should be relatively equal. I'm not going to pull out a micrometer and check. If it's more than 3 or 4 millimeters, I will notice with my naked eye, and I might circle and say, aren't these supposed to be the same? But if you've identified it in the problem as the same, then no problem, right? It's just a way of helping you get started, really. A girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. Diagram the forces acting on the girl. So you're going to have, once again, now on this one here, you may have wanted to draw in the surface. That is considered acceptable. Here, there is no surface, so we've got weight force down, and the actual answer has 2 separate forces that they label as FT, or tension forces. It's not technically a normal force, because there has to be a surface there. And the sum of those 2 arrows, like the length of those 2 put together, should equal the weight force, right? Should be balanced. Otherwise, she'd be either rising or falling. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it falls. Neglect air resistance. So there is no air resistance. So you should just have gravity. That's all you should have. A flying squirrel is gliding, no wing flaps, from a tree to the ground at constant velocity. When you see that in this type of problem, what does that indicate? Constant velocity. So a big flashing light. Warning. There's a net force of 0. Well done, Jake. The net force is equal to 0. So it says consider air resistance, diagram the force acting on the squirrel. So you should have weight force, and what are we going to call it? Air resistance or friction or something like that, right? And they should be equal. Now you might say, well, a flying squirrel is going sideways. Don't I have to show that somehow? Doesn't there have to be some sort of arrow going forward showing that it's moving forward? And the answer is no. There's no force pushing them forward. Is that what you were talking about earlier, Jake, you and I?
Yeah.
There is no force pushing them forward. They just happen to be already moving forward. Remember, Newton said that an object in motion stays in motion, doesn't need a force to keep moving. You might say, well, Mr. Bennett, there's like some air resistance backwards, or maybe it's like at that angle. And that would be true, but then their velocity would not be constant. And in this imaginary physics world, the air resistance is only up and down, not sideways. Right? Yeah, the world is kind of but it's there to just make things a little simpler, right? A rightward force applied to a book in order to move it across a desk with a rightward acceleration. Consider frictional forces. Neglect air resistance. Diagram the forces acting on the book. So it's moving with a rightward acceleration. Acceleration, big flashing red light, warning, warning. Net force is not 0. Consider friction. It's on a desk, so we've got the surface. Weight force, normal force, and there's a rightward force. Now, do I show it as a push, or do I show it as a pull? Do you remember? Almost always a pull. It's not considered correct to show it as a push, even if it is a push. Okay, so we're going to have some applied force like so, and there is going to be friction. Now, in this case here, I would be looking for 2 things. I'd be looking for the normal force and the weight force to be equal, and I'd be looking for the applied force and the friction force to be unequal. Clearly make them unequal. Don't make them like 4 millimeters difference, because I can't tell whether that's just bad drawing or you're making it bigger. Make it like an inch bigger. Easily identified. A rightward force applied to book or move it across the desk at a constant velocity. Consider friction forces and neglect air resistance. Almost identical situation, with the exception of constant velocity. These guys are the same, and this time the applied force is equal to the friction force. Why? Because it's moving at a constant velocity. Right? College student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram of vertical forces acting on the backpack. Weight force. Is there a normal here? There's no surface. It's one strap. So I think it's just FT, just a tension force. And those again should be equal. Number 8, the skydiver. Descending with constant velocity. Consider air resistance. Oh, I somehow lost my... It's going to be exactly the same. Weight force, air resistance, constant velocity. Force applied to the right to drag a sled across loosely packed snow. That's code for... There's some friction. There's rightward acceleration. Weight, normal force, applied force, whoops, applied force, small amount of friction. If it said hard packed snow or ice, then they're kind of implying that there's no friction, or very little. And number 10 is always the one that causes grief. Let's see how you guys have done with it. Oh, I'm getting kind of... What does number 10 look like? I'm going to take Randy's hand signals to represent weight force. Anything else, Randy? Just shaking your head, no. Anybody want to put another one in there? Do I need some angle, some arrow showing that the football is going up? There's no force making it continue to move. An object in motion stays in motion. That is it. That is it. There is only gravity acting on it. It says neglect air resistance. If you were to not, if you wanted to add in air resistance, it would probably be right there, because it says that it's already been booted and it's moving upwards. But if you neglect air resistance, then the diagram looks exactly the same whether it's going up or whether it's going down. Okay? Remember, an object in motion stays in motion. Car is coasting to the right and slowing down. Weight force, normal force, slowing down. Coasting means no applied force, only friction. Mentally give yourself a score. I would say 1 to 4, 1 to 5. Let's go 1 to 5. How well did you do on those? And I care, but I'm not going to record after. Are we good? All, yeah, give me, 4 or 5s. Good? Okay, awesome. Net force. Not that kind of force. I wish I was a Jedi Master. It would make teaching physics a whole lot more fun. But that's what would make it fun. Be all these discrepant events. You know that whole thing about what goes up must come down? I could totally debunk it. It'd be awesome. Only. Okay, so you can write down what you need to, whatever you need to do to make this stick in your head. A lot of this is just sort of reminders for me to say certain things and explain certain things, right? So don't feel the need to write down every single word, please. In the expression F equals ma that you've probably seen right from grade 9, I think, right? The A can be interpreted as the total resultant acceleration. We probably gloss over quite a bit in grade 9 and 10, and maybe even to a certain extent in grade 11. And to be perfectly frank, we're glossing over certain things right now in grade 12. It's just the way things work, right? We'll add in all the details later. You know how like in chemistry you learn about the Bohr model, and then as you get to grade 12, you guys in grade 12 chemistry yet? Talking about the orbitals? Okay, so right, we're adding details more and more. You're one of the special ones that knows about orbitals, Peyton. Oh, okay. So anyways, the A can be interpreted as the total resultant acceleration which a body receives when acted upon by some total force whose magnitude and direction are given by F. Generally, in grade 9, we just give you a force of 10 newtons is applied to a 2 kilogram object. What is the acceleration? Well, that's not really how it works, right? Because there's going to be friction and there's going to be air resistance and there's other forces. So really, the A is the total resultant acceleration of F, which is really a net force. The F is net force and the A is the total resultant acceleration. Sort of adding layers of complexity on it, which is kind of what I'm saying in this next slide here. Since force is a vector quantity, the total force acting upon an object is the vector sum of the separate forces that are acting. It is usually called the net force. Whoops. That was weird. Called the net force, where F net is equal to F1 plus F2 plus F3 plus F4 and so on and so on and so on, where there are multiple forces. Okay? Is this a formula that you need to write down and memorize? No, it's just saying add up all the forces. It's not really a formula, right? Whatever force 1 and force 2, those are not even going to likely be numbered in your situation. It might be like applied force plus friction force and so on, right? So don't try to come up with a way to memorize that. It's not really worth your time. Here's an example. Probably one of the simplest examples you'll ever see. Probably not worth the micro cents of pencil that you might use to write it down. Feel free to go ahead. Johnny and Billy are playing tug-of-war. Each is pulling with 75 newtons. You probably saw something like this in grade 9, right? So there's our free body diagram. Notice that I've conveniently left out the weight force and the normal force. Did I do it on purpose? Probably not. Does it matter? Weight force, normal force. Did I need to include them? No. Generally, when there's sort of a left to right motion kind of thing, we basically ignore the vertical forces. We know that they're going to be balanced, right? We're smart enough to just say, oh yeah, no, it's just a waste of time. Yeah, we know that, right? For, not simplicity, for completeness sake, you should probably include them. Am I going to be looking for them? No. Let's just move on. So F1 is 75. They're pulling, each is pulling with 75 newtons. They're pulling opposite. So 75 plus or minus 75, net force is 0. What is this object doing? Is it at rest or is it moving? Say that a little louder, sir. Depends on what it was doing before, doesn't it? Remember that whole discussion in grade 11? Well, it depends on how frustrating it was. Now, generally, I'm sure you imagine in your mind Johnny and Billy, two little kids, pulling on ropes, right? And the thing ain't moving, right? But it could also be doing what? It could be moving sideways, but then, of course, they would also have to be moving sideways with it, wouldn't they, right? So it's quite likely at rest, but that's not necessarily true. That's an example of a net force problem. This time they're doing what? Pulling in the same direction. So we're not gonna subtract, we're gonna add. Okay, so the forces are in the same direction, so of course we are not going to subtract, right? Pretty simple, right? No real sense in writing that down, I think. I'm just showing you how to sort of solve a net force problem here, right? Could we label this as FB and FJ if you want? Billy and Johnny? Absolutely. Okay? In real situations, friction is often a force that reduces the net force. This results in the formula F net is equal to FA plus FF. Hold on there, Mr. Bennett. Shouldn't we be subtracting the friction force? The friction force is negative. And this is really, this sign here, even though it looks like plus, it's really vector FA, vector addition FF. Does that make sense? Not regular addition, vector addition. Okay? So being in the opposite direction will have a negative sign associated with it. So it should maybe be rewritten as FA vector addition FF. And I guess there could be some special sign for vector addition, but that would just make things confusing. Oh, I should have the negative there. Okay? So just be aware of that. I'm just going to write things this way, FA plus FF, and then I'm going to use the negative sign of it. Okay, let's go ahead and write this one down. Pretty straightforward. You probably did in grade 11. Again, just a refresher. Suppose a 10 kilogram object is being accelerated by a 10 Newton force. The force of friction is 6 Newtons. What is the resultant acceleration? If you want to abbreviate some things here, that would be just great. Okay, I'm not expecting you to be too astounded by anything here. So, what are my steps? I'm looking for the acceleration. Before I can get acceleration, I need the net force. Let's solve for net force first. F net is equal to applied force plus friction force. Applied force is 10, friction force minus 6, giving us a net force of 4 newtons. Now I can go to F net equals ma. F net is 4, the mass is 10, and the acceleration is 0.4 meters per second squared. Let's try a little harder one. A 3 kilogram object is going 5 meters per second at t is equal to 0 seconds. 4 seconds later, it's traveling at 2 meters per second. What force of friction is acting? No, it doesn't want it. We got a mass. What force of friction is acting? How am I going to get friction force? Think backwards here. What's the last formula that we're going to use? Likely going to be F net is equal to FA plus FF. Is there an applied force here? Do I need to pause and wait for you guys to jot the question down? Jake's right. It doesn't say there's an applied force. Can the net force just be friction? Why not? Net force just means sum of all the forces. If there's only one force, then that's what it is. Okay, so I need to come up with the net force. I'm going to have to use the bridging formula, and I'll explain why I call it the bridging one in a bit. I'm going to have to use F net equals ma to get F net to get to there. Now I'm lucky. Where's my... Right now I'm just looking for my cursor. Curse that disappearing cursor. It is clearly a bunch of junk here. I see it. There it is. What I was going to say was I can just drag this over here and sort of work things backwards, right? You unfortunately have to sort of think things through and figure out the order that you're going to do them. How am I going to get F net equals ma? I got the mass. What do I not have? I don't have acceleration. I got to solve for acceleration somehow. What do I have? I have an initial velocity, and I have a time of 4 seconds. How am I going to get A? Oh, and I have a final velocity, don't I? How am I going to get A out of VI, VF, and T? You can use that one from grade 11, or we can use the new and improved.
It's really all improved.
No, it's just like the commercials, right? They say new and improved, but that's just so they can charge you more. I'm not charging you any more for this. You like that old product, right? iOS 7. Is there anyone happy with iOS 8 yet? No?
You can leave group chats.
What's that?
You can leave group chats.
Okay, so let's use this here. VF is 2, VI is 5, A, my time is 4 seconds. So my acceleration is, and Brandy's going to say, that's exactly the same as A equals delta V over delta T. 2 minus 5 all over 4, or minus 0.75, right? Then I'm going to take that, and I'm going to plug it in over here. F net is equal to ma, so that's going to be 3 times minus 0.75 is minus 1.5, minus 2.25. Check my math for me. And now I'm going to take that, and I'm going to plug it into... Oh, actually, do I need to plug it in here? Can I just leave it like that? I probably should, for the sake of I'm thinking about it as a student. You're showing me that you get the net force of the friction force. You should probably have something like friction force is minus 2.25. At the very least, you should have that step, right? I don't necessarily need to see this, but at the very least, don't just write minus 2.25 under here, right? Tell me that you know it's the friction force. Be complete, be thorough, is what I'm saying. Any questions about that one? That's pretty straightforward, right? I mean, again, all of these, we're just sort of revisiting net force here.
Is that minus 7.5 or minus 7?
Minus 0.75, right there? Yeah. What makes this one harder?
Oh,
Is it harder? Yeah, it's harder. There's an angle involved, right? Force of 50 newtons is applied to a 10 kilogram snow sled at 30 degrees above horizontal. The force of friction present is 18 newtons. Find the horizontal component. I gave you the steps, though. Find the horizontal component, find the net force, find the acceleration. I'll give you a moment. Okay, let's have a look here. So find the horizontal component, FH. So we're going to have to go into this triangle here. And that FHFV thing should make a whole lot more sense to you now that you know how to add vectors by components. Right? So what is the horizontal component here? It's adjacent to the angle. I know the hypotenuse, so it's going to simply be 50 cos 30. Will it always be cos? The horizontal component, will it always be cos? I will say that at 99% of the time it will be cos. Do you know why? And it doesn't have to be, but there's a reason why. 99% of the time. Because they almost always give you what angle? They give you that one, right? Have you ever seen it where they draw it like this and then they give you this angle in here? Not usually, right? Usually when the thing is moving sideways, they give the angle in relation to above the horizontal. So when they do it that way, it's always going to be cos. If they do it this vertically way, well then it's going to be sine. But it very rarely happens. Okay, so here it's going to be 50 cos 30. $43.3, right? So of the 50 newtons, only 43.3 does actually what? Pull it sideways. What happens to the other bit? It pulls it up. What does that do to friction, the lifting up? Did you guys do, in grade 11, remind me, do you guys talk about frictional coefficient?
Yeah.
Yeah, okay. So we're going to get more into that in the next day or so, but it would actually do what? Reduce the friction here. But in this particular situation, I've already given you the force of friction. I've sort of simplified that step, okay? But that will come into play, and especially in the lab that we do. So my horizontal component is 43.3. So now my net force is my horizontal plus my friction. Again, can we ignore the vertical? Yes, because we know they balance out. So 43.3 minus 18, 25.3. And find the net force, which we did. Find the acceleration. I always like it when the thing weighs 10 kilograms because I don't need to calculate it. No problem, right? How come I call, I'll just take a couple more minutes of your time. How come I call F net equals MA the bridging formula? Anybody know why? Okay, that's not why I call it that. You can call it that for that reason if you want. It connects two families of formulas. All of this stuff here, like mass is a scalar, right? But acceleration leads to stuff like VF equals VI plus AT, and D equals VIT plus 1/2 AT squared, and VF squared equals VI squared plus 2AD, right? It leads into all the kinematics. But the FNet is all the dynamics formulas, all the force formulas, okay? So the only way to get things like distance and final velocity, you have to go through FNet equals MA. That's the only way to get from forces to all those guys. That's why I call it the bridge apart. I guess it could look like a bridge too. Oh, like if I had to do this. If it started from rest, find its displacement after 4 seconds. Yeah, exact same one, right? Let's just add it in. So if it started from rest, 0 plus 1/2 my acceleration, which was 2.53, and 4 seconds squared. Oh yes, a couple people missed that on the test. Make sure you get that right. I get 202, is that right? That seems awfully large. 202 meters? Okay.
I got 20.3.
Did I do something wrong? Oh, I know why. I didn't have 2.53, I had 25.3 in my calculator, and I did that part in my head. So you're right. That seemed big. 20.5 meters. Thank you, Ashley. Yes, I always hope that there's somebody named Luke in the class, so I can tell them to use the force.
When's the last time you had a person?
Maybe Luke Fafard, maybe.
Last time I got.
Oh yeah, Luke Bouchard last year, right?
But it's not sponsored.
No, I know.
His first name is Lee. So.
What are you, his lawyer?
Yeah. And he's my math dude.